Hi, my name's Francesca.
And I'm George.
We are from Mr. Morgenroth's third period math class.
And today we are going to be talking about Chapter 5 in our pre-calculus textbook. We will be covering the unit circle approach to trigonometric functions.
Let's get started. First, we need to go over some key terms. The unit circle is the set of all points at a distance from 1 from the origin. It has a radius of 1 and is centered at the origin in the xy plane. Its equation is x squared plus y squared equals 1.
The terminal point is the distance traveled from the point 1, 0 around the unit circle to give us point P, x, y.
We use reference numbers to help us find a terminal point. The reference number t is the shortest distance along the unit circle between the terminal point determined by t and the x-axis.
In order to find the terminal point P determined by any value of t, we use the following steps. 1. Find the reference number t. 2. Find the terminal point QAB determined by t. And 3. The terminal point determined by t is point A plus or minus A, comma, plus or minus B, where the signs are chosen according to the quadrant in which the terminal point lies.
Alright, we got through section 1. Let's see if we can get to the harder stuff now. We are now going to introduce trigonometric functions to the unit circle. Allowing t to be any real number and having pxy be the terminal point on the unit circle determined by t, we define the trigonometric functions as sine t equals y, cosine t equals x, tan t equals y over x, cosecant of t equals 1 over y, secant of t equals 1 over x, and cotangent of t equals x over y. Keep in mind the restrictive domain. The denominator cannot equal 0.
In order to compute other values of the trigonometric functions, we first determine their signs. The following box shows the signs of each of the functions in each quadrant. In order to make this easier, you can remember the following mnemonic device. All students take calculus. In order to figure out the sign of secant, cosecant, and cotangent, it is important to know that secant x equals 1 over cosine x, cosecant x equals 1 over sine x, and cotangent x equals 1 over tangent x.
Each function also has the property of an even or odd graph. Sine, cosecant, tangent, and cotangent are odd functions, while cosine and secant are even functions. Alright, now that we have all the basic information covered, it's time to get to the fun stuff.
First, we are going to be looking at trigonometric identities. This is how different trigonometric functions are related to each other.
The reciprocal identities are as follows. Cosecant of t equals 1 over sine of t, secant of t equals 1 over cosine of t, cotangent of t equals 1 over tangent t, tangent t equals sine t over cosine t, and cotangent of t equals cosine of t over sine t.
We also have Pythagorean identities. They are sine squared t plus cosine squared t equals 1, tan squared t plus 1 equals secant squared t, and 1 plus cotangent squared t equals cosecant squared t.
Let's prove some of these identities. By definition of a terminal point pxy on the unit circle, and given that cosine of t equals x and sine of t equals y, we can use the equation of the unit circle to find that sine squared of t plus cosine squared of t equals 1.
To find another identity, you can divide that value by cosine squared t. Doing so would get you tan squared t plus 1 equals secant squared t.
Okay, that's all for section 2. Now let's take a look at section 3. Alright, in order to understand the behavior of certain functions, it is helpful to graph them and their transformations. The functions sine and cosine have a period of 2 pi. Sine of t plus 2 pi equals sine t, and cosine of t plus 2 pi equals cosine t. Imagine a terminal point on the unit circle. To make one full lap around the circle, one needs to trace the entire circumference of the circle, which would be 2 pi. Make sense?
Here is a graph of y equals cosine x. Let's try out some transformations. First, let's look at what happens when y equals negative cosine x.
It flips across the x-axis.
Now let's look at what happens when y equals 2 plus cosine x.
Now it's vertically shifted up 2 units.
Lastly, let's try multiplying cosine x by different numbers. If we multiply it by 2, the graph seems to condense because the y values are getting bigger, while x values stay the same.
However, if we multiply x by 1/2, it stretches because the y values are smaller while the x input stays the same.
Based on our observations, we can say that the sine and cosine curves y equals a sine kx and y equals a cosine kx, when k is greater than 0, have an amplitude of a and a period of 2 pi over k.
Alright, that's it for section 3. Now let's move on to section 4 and try out some other trig functions. To graph y equals cosecant x and y equals secant x, we use the reciprocal identities. Y equals cosecant x equals the same thing as 1 over sine x, and y equals secant x also equals 1 over cosine x. When we input values, this is what their graphs look like. Therefore, we can say that y equals a cosecant kx and y equals a secant kx with a period of 2 pi over k.
Lastly, let's talk about transforming tangent and cotangent graphs. These are a little bit harder because they have asymptotes. The functions y equals a tangent kx and y equals a cotangent kx have a period of pi over k. One complete period of the graphs of these functions occurs on any interval of length pi over k. That's it for section 4. Now let's move on to section 5.
Alright, we've graphed trigonometric functions, their reciprocals, and their transformations. Now let's try some inverse functions. The inverse sine function, called arcsine, is a function denoted as sine to the negative 1, with a domain of negative 1 to 1 and a range of negative pi over 2 to pi over 2. Arcsine x equals y also means sine of y equals x. Therefore, y equals arcsine x is the number in the interval negative pi over 2, pi over 2, whose sine is x. It looks like this.
The inverse cosine function is the function cosine to the negative 1 with domain negative 1 to 1 and range 0 to pi, defined by inverse cosine x equals y and cosine y equals x. It looks like this.
The inverse tangent function is the function denoted as tan to the negative 1 with a domain of all real numbers and a range of negative pi over 2 to pi over 2, and it looks like this.
Lastly, to define the inverse function of secant, cosecant, and cotangent functions, you have to restrict the domain of each function on a set on which the function is 1 to 1 and contains all its values. Let's flip through these graphs to see what they would look like.
Alright, that's it for section 5. Now let's go to section 6. Alright, our last topic is harmonic motion. Harmonic motion is a model of periodic behavior that repeats over and over again. These repetitive patterns are very common in nature. You can find them when looking at patterns of tides, animal populations, the daily rising and setting of the sun, and many more. Another common example is motion caused by vibration.
Trigonometric functions model periodic behavior. For example, the motion of a vibrating mass on a spring can easily be drawn by a graph of y equals sine t. Take a look.
This is how we summarize periodic behavior. If the equation describing the displacement y of an object at time t is y equals a sine omega t or y equals cosine omega t, then the object is in simple harmonic motion.
For these examples, the amplitude would equal the absolute value of a, the period would equal 2 pi over omega, and the frequency would be omega over 2 pi.
This is known as simple harmonic motion, meaning it is assumed to oscillate in a frictionless environment. That case is more hypothetical, though. In reality, the presence of friction causes the motion of the spring to slow down until it eventually stops moving. This type of motion is called damped harmonic motion.
Given the equation describing the displacement y of an object at time t is y equals ke to the negative ct times sine of omega t, or y equals ke to the negative ct times cosine omega t, then the object is in damped harmonic motion. The damping constant is defined by the constant c, the initial amplitude is k, and the period is 2 pi over omega. All right, that's it for Chapter 5.
We hope you learned something. We had fun being here.
Mr. Morgenroth, please give us an A.